you the problem of the drop of water, drop of rain, better said. And in this problem, we are going to study like two regions. The first one is the formation of the drop of water. And the second one is the rain itself. So we're going to study this with differential equations, of course. We're still aiming at studying first order differential equations. So we will retrieve a first order differential equation that's gonna give us like a very simple model of this drop of rain. So what we aim at is calculating the velocity of a drop of water that is coming out of a cloud before the rain starts. So our aim is to calculate the velocity of a drop of water when it's formed in a cloud right when it's gonna start raining. My handwriting is not the best, I'm sorry. So, well, let's imagine here we have our cloud and we have two regions. First, as like up to a certain level, we're gonna consider that by condensation, the drop is gonna be forming until here. And then we will consider from this height to start raining. The rain itself. So we have some hypotheses to put to solve this problem, because otherwise it could be really, really complicated. So the first hypothesis that we're gonna have is that the mass of the drop of water is gonna increase as it falls down. As it falls down. Because we're supposing that we are in a kind of atmosphere that is condensating. So it's condensating atmosphere. Okay. Another hypothesis is that the variation of the mass of this drop that is gaining volume as it's going down is going to be proportional to the surface. So the variation of mass of the drop of water is going to be proportional to the surface of the drop. And by the way, we're going to suppose that this drop is going to be a sphere. So the surface will be that one of the sphere. So our drop is going to be spherical. And well, the third hypothesis is that the only force that the drop at the formation of the drop, we're still in the formation process, the drop is only subject to gravity. Okay, so bearing in mind these three hypotheses, we can start construct our model. So let me start with them, how to rewrite this hypothesis. So first of all, let me consider the density to be equal to 1, okay? So that means that if my density equals to 1, the mass of the drop divided by the volume is going to get me that the mass is going to be the volume. And the volume, we said that it's going to be a spherical. So it's going to be 4/3 of pi radius to the third power. Okay, so we have that on one part. So that's the mass. And how the mass is related to the radius. That's one. The second thing is that we know that the variation of the mass is proportional to the surface of the drop. So what is the surface of the often spherical volume? Well, the surface is 4 times pi radius square. Okay, and this is a constant of proportionality. Okay, so if we combine these two, we have in mind that our mass on one hand is this, then if we derivate the mass with respect to time, it's gonna give us the change of the radius with respect to time. And these two obviously have to be the same. So by pure comparison, that means that the constant of integration, in this case, these 3's go away. Sorry, this is square. This is differential of r with respect to t. So in this case, we just get to the conclusion that the radius varies in time and at a constant rate. That is that k that we introduce. So that's another thing that we have to bear in mind. And from the third hypothesis, we know that the drop is only subject to gravity. So let's say then that all the force that the drop is subject to is that going to be that one of gravity. So depending on the convention that you use, the gravity, you can use it positive and negative depending on the coordinates that you're going to use. So to avoid coordinates in this case, I'm just going to put the absolute value of g, okay? So it could be minus g or plus g. And here, this would be the force on the left-hand side. Bear in mind that here the mass depends on time. So it's varying. Okay, so now let me rewrite this. So we're going to perform this differential with respect to t of the mass times the velocity. Okay, so vt is velocity. Okay, so if we put the mass, actually, we have it here. We said that the mass is 4/3 of pi radius to the third power. Then we have that the mass is 4/3 of pi radius to the third power times the velocity. So here the constants can go out, and we basically just have to derivate the third power of the radius times velocity. Okay, and this has to be equal to the mass, which we can already put that we know that is 4/3 of pi radius to the third power the absolute value of the gravity. So here the 4/3 go away, the pi go away, and here we get to this following equation. Realize that here we actually want to know how the velocity varies in time, but we also want to know what's the velocity of our drop depending on the radius that our drop has. So here we have velocity depending on time. So what we have to do is just to introduce the chain rule to change the derivatives to archive what we actually want, which would be the velocity in depending on the radius. So if we do that, we simply have to use the chain derivation rule, and that means that we have to introduce the radius variable. That would be the chain rule. But here, focus on something. Realize that the r changes with t as a constant, which is basically this claim. So we already have here a new result, that k times differential with respect to r of the third power of the radius times the velocity, it's going to equal the mass, mass we had already gotten rid of it, it's gonna equal the mass times it was gravity, right? With the third power of the radius. So now what can we do? We can just integrate. So now we're going to integrate the expression from a radius r0, which is the initial radius, and a radius at a time t of this differential of r of this quantity. And this is going to equal the integral from radius r0 to r of our radius and the absolute value. So what do we get here? Well, we simply have here that on the left hand side, we'll just have our expression in the limits of integration. And here we'll have r to the fourth power times g. And I'm not going to put there the constant of integration because I'll put it on the left hand side. So here we'll get that k times the radius at a specific time with the velocity minus the radius in the initial instant that will correspond to an initial velocity will be equal to the radius times g. So now we can put everything to the right hand side, and also if one wants to get like a more determined expression, we can do something else. Let me go back, because maybe it's better to introduce that velocity depending on the radius, also depending on the initial radius in a different way. So let me put the constants of integration differently so we can get to the usual expression that we normally find in the books for this velocity. So I'm integrating, but I'm going to put a constant of integration actually here. So we're going to fix that constant. So again, I go back to my integrals. And this other integral. Okay, so now what do we have? Well, we have here that the integral on the left, we can leave it as it was. Let's just put in we use the barrel rule with the two limits. And actually here, I'm gonna put the two limits as they are. So from here, I get the r at any time minus the r0 and the velocity, that is the initial velocity, and this is gonna equal r to the fourth power times g minus r0 to the fourth power divided by 4 times g. Okay, so we can get this expression. So here, if we just get what dv, which is this one, how it can be written in terms of the rest of the expression, one can write simply r0 divided by r to the third power and multiplied by b0 plus the g. I'm gonna put it as common factor divided by k, and this is r divided by 4 minus r0 to the fourth power divided by 4 r to the third power. And there's another way of rewriting this expression. Sometimes it can be rewritten, it can be shown in books as this. So the r0 divided by the r, because this is going to be convenient, as you will see. So these will be how the velocity of a drop that is just formed under hypothesis 1, 2, 3, how the velocity of this drop changes with the radius, where r0 is the initial radius. So now if one wants to see what's the velocity with respect to time, what we can basically do here is it's another consideration that is pretty common, and it's that r is gonna be way bigger than the initial radius. How is this possible? Well, experimentally can be determined that initial radius can be micrometers, and the radius can get to be of the size of millimeters after the formation of the drop and in the initial region. So basically, we can suppose that r is going to be way greater than r0. So if we take the limit when r goes to infinity of our velocity, we'll get like the initial term will go to 0, and this one will go to 0 as well. So we'll just end up with modulo of j divided by 4k multiplied by r. But also we knew that the r with respect to time is changing as a constant rate that was q, so r can be considered as q times t. So this can be rewritten as g q times t divided by 4k, and we can get to an approximate equation of how the velocity where the radius becomes big can be represented by this simple equation. The second region will be just like once the drop has been formed, or we have rain. So when we have rain, we have to to bear in mind a very simple supposition that is going to be the some kind of friction force. So basically, how is the rain gonna happen? Oops, the rain gonna happen. So the rain afterwards will be something like, now the mass, we're gonna consider it fixed because there's no formation anymore. The drop gets to a fixed mass at some point. So then the velocity is going to start changing with time, but it's going to change in a very different way. Well, it's going to be the mass that is going to be a constant, and the g that is going to be, in principle, we're just going to put absolute value depending on how you want to solve this problem, plus a force that is going to be a friction force, probably from the wind. So bear in mind that depending on how you put g, the friction force is always going to be the opposite sign. And it has been proven also experimentally that one can put like the friction as a function of the velocity, and it can be either linear or it can be quadratic if you want to be a bit more accurate. And this kind of equations, we know how to solve them. Okay, so if it's just v or v squared, it's a very simple function, and actually the equation is separable, so it would be really easy to fix. So depending on the initial conditions that they give you, you can put different f's and try to solve the equation. But my main issue was to show you how to produce a drop and how the formation process is made by simple hypotheses, which are hypothesis 1, 2, and 3.